Okay, welcome to part 3 of the presentation for chapter 13. Seems like it's a summary, but it seems a little bit longer than a summary as well. It's an odd feeling. Okay, well, here we go. You've already seen the UEQ, so I'll just move on. Here is the second lesson question, and I believe you've already had this, so I'll move on. And I believe we had already talked about this in the previous part 2 of the colligative properties objectives. And so if you need to, you can pause, of course, at any slide and write down anything that you need. Otherwise, I will move on. Okay, check this out. This is an interesting diagram that shows colligative properties. And here's what this is showing. So if we follow the dark line, this dark line may represent water, for instance, in its pure form, so a pure solvent, water. And then you take a solute of some sort, dissolve it in water, and so now you have a solution. So what happens to this solution? Well, what this chart is telling us is basically the point at which this liquid would freeze and at which it would boil. Okay? So when you you make a solution, what you will find is that the solution actually will have a different freezing point and a different boiling point. And so if we take this particular line down here, this line would represent the normal freezing point of water. This line over here, if we follow it all the way down, is the normal boiling point of water, and there would be 100 degrees in between here on the Celsius scale. Well, by the addition of the solute, notice what's happened to the freezing point. The freezing point now is down here. It's lower. Now, how much lower? I don't know. We don't have numbers, and it's not really important that we do. But the freezing point is now lower. This is called freezing point depression, where the freezing point is simply lowered by the presence of a solute, making it a solution. What about the boiling point? Well, if we come up here to the boiling point, remember this is the normal boiling point. Here we have an elevated boiling point. It's now increased. This liquid will boil at a higher temperature than normal water simply by the very presence of that solute. So that's called boiling point elevation. These are 2 of the 4 properties that we will talk about going forward. And with a little bit of knowledge, we can actually calculate what this temperature would be for water and other solvents. Okay, colligative properties. First property up for bid is vapor pressure lowering. Okay, so colligative properties, vapor pressure lowering. Properties that will depend upon the concentration of the solute particles, but not upon their identity, are called colligative properties. Basically, we take the pure solvent and we compare it to the solution. One of these properties is vapor pressure lowering. By the addition of what is called a non-volatile solute, will have the action of lowering the concentration of water molecules at the surface of the liquid. Thus, it will lower the number of water molecules that can enter the gas phase, because they can only enter the gas phase at the surface. And it will lower then the pressure above the liquid for the water molecules that are gas pushing down on its own liquid. So that would be vapor pressure. And with less water molecules above, there's less pressure. And so vapor pressure lowering is how that's going to work. Now, this word non-volatile, just to make you aware of that, non-volatile, I think we've talked about this in class before, but the word volatile, while it has like normal context, if we were just talking in the cafeteria, in chemistry and in science generally, volatile simply means that the substance, whatever it is, will tend to become a gas very easily. So basically it vaporizes very easily. So by saying non-volatile, we're simply indicating that this substance does not easily become a gas. And that's important because if you want to have it enter water, then gases, while they can enter water, are not likely to stay there. So we're looking for some other type of solute. Okay. Okay, so this is an image of pure water on the left and a solution on the right. So we have a lot of vapor pressure above this water solution, or it's not, excuse me, just above this sample of water over here. It's pure solvent. And all the water molecules are at the surface. Rather, I should say, only water molecules are at the surface. There's 100% water molecules at that surface, and so therefore any of them can enter the gas phase and create vapor pressure. When you have a solvent present, or a solute present in your solvent, the solute actually takes up space at the surface, and because it takes up space at the surface, then there are fewer water molecules that can actually enter the gas phase, simply because there are fewer water molecules at the surface. Okay, one of the other colligative properties of the four that we'll look at is what is called freezing point depression, and we've already talked about this. So on this particular slide, what are we saying? The addition of a non-electrolyte solute. So a non-electrolyte, so remember with this, when you put this solute in the water and dissolve it, it will not create ions, and so therefore it will not conduct electricity. So if you put 1 mole in, you have 1 mole of solute floating around, and that's all you have dissolved. You put 2 moles in, you have 2 moles floating around. Unlike, remember, with electrolytes, you put 1 mole of salt in, and you stir it and dissolve it, but you have 2 moles of ions floating around because the NAs and the CLs split up. So it's important about this non-electrolyte, because non-electrolyte, for every 1 you put in, you have 1 floating around. Electrolytes, for every 1 you put in, you minimally will have 2 floating around. Otherwise, it'll be even more than that. And that will affect things, because that's a concentration issue. So what does this say? Well, the addition of a non-electrolyte solute will lower the freezing point of a solvent. A 1 molal solution, so remember that's 1 mole of solute per kilogram of solvent, well, it says right there, to water will lower the freezing point by 1.86 degrees Celsius. So if water freezes at 0 and you have a 1 molal solution, it's going to freeze at negative 1.86 degrees Celsius. If you instead have a 2 molal solution, it will double the freezing point lowering, and it'll take it down by an additional 1.86 to get it down to a negative 3.72, which is again twice that. So this leads to a constant that we call the molal freezing point constant, symbolized Kf. This is a uppercase K, and that's a subscript lowercase f, so Kf. And basically, each solvent that can dissolve anything will have a freezing point constant of its own. It turns out that water is negative 1.86. Other substances have their own freezing point constants. But basically, it's just standardized to a 1 molal solution of a non-volatile, non-electrolyte solute. How low will that take it? That becomes then the constant. So how low can you go? Can you take it all the way down and have something that just won't freeze? I mean, that's a very good question. You know, how low can we take this freezing point down? Well, basically, you're going to be able to take it down until you have a saturated solution. And that's where you're going to stop. So you can't take something all the way down and never have it freeze. You won't get there. But you will saturate a solution, and once you've done that, you've maximized the ability of the solute to interfere with the natural freezing process and to take that freezing point as low as it can possibly go. Now, an interesting aspect of that is typically when the temperature is lowered, solubility actually decreases. And so you are going to be able to saturate a solution with less solute the colder it gets. And so it's you know, if you're trying to get the freezing point down, you're going to actually fight that. Okay, well, how can we then predict this freezing point depression? Now, typically for many of the examples and some of the homework that you may have, whether it's in your book or on a worksheet, typically deal with water. We don't have to always deal with water as a solvent, but it's convenient and it's all around us. So water typically comes up as the example to use. So looking at water, the freezing point depression, which we will use delta TF for the freezing point temperature, I guess. And the delta is the difference in. So it's the difference between the freezing point of the pure solvent and the solution involving a non-electrolyte that we have dissolved in the solvent. So the formula is right here. Delta TF, change in the temperature from the freezing point to the new freezing point, so that's what that is, equals the constant freezing point constant KF times the molality. Okay, times the molality. So the freezing point constant times the molality. KF units are degrees Celsius per molal, so the units work out very well for that, of course. For water, the molal freezing point constant for water is negative 1.86 degrees Celsius per molal. And remember, you've got the notation for molality right there. Now, if you want to actually know the freezing point, so this will predict the difference in freezing points, and that's all it predicts. If you want to know the freezing point, then you have to subtract it away from and get the difference from the actual freezing point. Now for water, this works out well because the answer to this question is the freezing point of the new solution involving water, because water is at 0. And so it'll just be, that from 0. However, with other solvents, you're actually going to have to do some subtraction there to figure out what the actual freezing point is. So read the questions carefully before you actually attempt them to understand, are you looking simply in the difference in the temperature, from what to what, or are you actually looking for the new freezing point itself? So be careful on that. Remember, you have a mini guide, you have a text, you have a bunch of questions that you can be working on to do some of this math. And of course, I will ask you to do some of these calculations on the test. Okay, so here's an example. It looks like so freezing point depression, FPD. Predict the temperature at which a 65-gram sucrose, sugar solution will freeze if you dissolve 65 grams into 750 milliliters of water. Remembering that the formula is the difference in temperatures will equal the constant KF multiplied by the molality. And here's the information for water. And water's normal freezing point is 0 Celsius. And all of this works with Celsius, so there's no need to go to Kelvin on any of this. All right, so what will the work look like? Here's the work. So I've simply rewritten the formula up here. I've written the information over here. And then I went ahead and I did my calculating my molality. So here's my molality, converting grams to moles for sucrose over the kilograms of water. Remembering it gave us the amount of water, and knowing the density, I can convert it to kilograms. So that was not, it was given, but it was more inferred. You had to calculate that. So this gives me my molality, so that's the M up here, all of this. And then I multiply that by the KF value, which is a negative, and you got to remember that negative sign, negative 1.86 degrees Celsius per molal. Molal will cancel with the unit up here, which is molal, and that will give us our delta TF. So you do the math, and the delta TF is negative 0.470 and a whole bunch of other numbers degrees Celsius, combining that with water's actual normal freezing temperature, and it looks like the temperature is negative 0.47 degrees Celsius. So that's what that sugar water will freeze at, and we could test that out. That's not a hard test to make. Okay, moving on. Okay, here's another example. We have a water solution containing an unknown quantity. Ooh, there's a mystery there. An unknown quantity of a non-electrolyte, and it's found to freeze at negative 0.23 degrees Celsius. So we're going to backwards calculate and figure out what the mole concentration of the solution is in order to make that solution freeze at that temperature. So it's just kind of working the question backwards. We're still using water, and so with water we have our KF value, and here is the information there. So let's see if we have a solution. Okay, so what I have done is I've taken my equation and I've rearranged it to solve for molality. Remember that the delta TF is a difference in it, so I want to make sure that I do my calculation. For water, it's easy for freezing point. Every other substance, you got to do some math for that. So negative 2,3 minus that gives me a delta TF of negative 2,3. So negative 2,3 degrees Celsius is this value right here. I'm going to take that and divide it by KF, which is always a constant because it's water. Here it is. If it's another substance, I look that up. So you do your division. Notice the negative signs cancel out because molality cannot be negative. there would, I'm not quite sure what that would mean, a negative molality. So it turns out that a 0.12 molal solution of a non-electrolyte, non-volatile solute will actually make that solution every time freeze at -2-3 degrees Celsius. Okay, moving on. Well, if solutes will actually lower the freezing point, they will also at the same time elevate the boiling point, and we saw that on that graph. So what does this say? Boiling point elevation, delta TB now, B for boiling, is the difference between the boiling point of the pure solvent and of the solution, assuming again non-electrolyte, non-volatile, so things are a little bit simpler, less to keep track of. Okay, well the formula you're going to notice is the same. Oops. Okay, so the formula is the same, except for the fact that I now have subscript of B for boiling instead of F for freezing. It is still K times the molality, but now I have a new constant. This is the molal boiling point constant. This number will be different, even for water. It's not a -1.86, because it takes a different amount of energy to get something to freeze as opposed to boil. And so you're going to always see a Kf and a Kb for the same solvent be very different numbers. Okay, so the units are the same for, it's a K value, constant, so the units are the same, degrees Celsius per molal. Kb is the molal boiling point constant. Delta Tb is the boiling point elevation. Remember, it's the difference in the temperatures, not the temperature itself. And here for Kb of water is a positive 0.51 degrees Celsius per molal. So if I had a 4 molal solution, it would raise the boiling point 4 times this. So 4 times 0.51 would give me 2.4. And then I would add that to the normal boiling point of water, which is 100 degrees Celsius. Here you will always have to do math. You're going to have to add the temperatures together if you're looking for the actual boiling temperature itself and not just the difference. And this says what? Try associated practice problems from the mini guide. So I would really refer you to that mini guide to try these. They work very similar to the freezing point questions, except you're boiling instead of freezing. Okay, a fourth, because we already talked about vapor pressure lowering. We talked about boiling, or well, in order, freezing point depression, and then boiling point elevation. So the fourth and final colligative property that we will talk about is called osmotic pressure. Now, if you remember from your biology days, whether it was 10th grade or if you've taken biology all the way up through, that osmosis is a movement of a solvent through a semi-permeable membrane from the side of a lower solute concentration to the side of a higher solute concentration. So I believe the flow is from hypertonic to hypotonic, if I remember my terminology. This is what happens in blood cells. There's osmosis in blood cells. There's osmosis, I believe, in plants as well. So basically it occurs whenever two solutions of different concentrations are separated by a semi-permeable membrane. Some kind of membrane that'll let one thing through and will stop something else. The cell wall is a very good example of a semi-permeable membrane. So osmotic pressure is then the actual external pressure that would be applied to stop the osmosis flow. And so that's all osmotic pressure is. What is that pressure needed to stop osmosis? Okay. So here is an example, this image probably right out of your book, where we have basically just a U-shaped tube. We have two solutions of different concentrations separated by a semi-permeable membrane. The semi-permeable membrane will allow the flow of water through the membrane, but it will stop the sucrose. And it can do it a number of different ways. Sometimes it could be literally just size. Other times it could be through some other action. So basically you go from, excuse me, from low concentration, or from high to low concentration. And so we have water flowing initially in only one direction, and then eventually as we see that this concentration goes from high and it becomes lower because water is moving in. The solute concentration doesn't change, so there's the same amount of solute on this side of the device. However, because we're adding more and more water, it's becoming more and more dilute, so this concentration is going down is what is happening. So from low to high, this concentration goes down. And as it goes down, notice because we're adding water, we're adding volume. Now eventually, this mass of solution has weight. And it's going to create pressure. And so that pressure pushing down will actually stop the flow of water through here to where it'll basically reach equilibrium, where there will be water actually flowing through the semi-permeable membrane, but it'll be flowing in both directions at equal rates. And this volume disparity will be able to kind of tell the tale that osmosis has occurred. Now, can we quantitate? Can we do math with osmotic pressure? Oh, yes, we can. Now, we're not going to have to do these calculations, but it is nice to know that we can do them. So let's just quickly take a look. And remember again, you're not going to do these calculations. Not hard, but you know, it's just beyond where we need to go with this. So check it out, quantitative osmotic pressure. Now, if you look at this, here's your ideal gas law, PV equals nRT. But because we're going to be talking osmotic pressure, we're going to switch out the P with the symbol pi. Now, this is not going to be 3.14 like in math class, but we're going to grab that Greek symbol, we're going to bring it over, and we're going to have it stand for pressure, in this case, osmotic pressure. So osmotic pressure times the volume equals the nRT value. Here are all of your symbols explained out. We can also do a little bit of arrangement where we can bring in the number of moles and the volume together to create molar mass. Excuse me, not molar mass, but molarity. Moles over volume, moles over liters. And so osmotic pressure could equal the molarity of the solution multiplied by the R value, the constant, multiplied by the temperature of the solution. Okay, so taking a look at a very, very crudely drawn J channel. So here we have a 1 molar solution, and here we have a 1.5 molar solution separated by a semi-permeable membrane. This side is hypotonic, this side is hypertonic. Remembering over here that pi is the osmotic pressure, and we could list it in atmospheres, millimeters of mercury, or any value for pressure whatsoever. So given time, what will happen is that the lower concentration will flow to the higher concentration through the semi-permeable membrane. So as the water, the solvent flows through, look what happens to the side. It originally started at 1 molar, now it's 1.2 molar. How did that happen? Well, remember the solvent is passing through the semi-permeable membrane, but not the solute. So the solute is staying behind. Well, this solute with less and less solvent becomes more concentrated. What's happening over here? Well, originally we started at 1.5 molar, but inflow of water through the semi-permeable membrane, the solvent. And the solute is not changing the amount, but it's adding more and more water to it. And because you're having more water, then your concentration is going down. Eventually, whether they equilibrate with exactly like what 1.25 or not, that will remain to be seen. But however, it's about a pressure. It's not about a volume. It's not about the actual molarity. It's about the pressure. And once this column gets so high, the down pressure, the pressure created on this side, will basically stop the influx and will create a system of equilibrium where water just flows through back and forth through the semi-permeable membrane. So the solvent moves through, it dilutes the one concentration. The concentration on the left is increased while the concentration on the right is decreased. The pressure will stop osmosis, i.e. osmotic pressure. Think about this. Calcium chloride has 1 calcium and 2 chlorines. Moving ahead. So if calcium chloride actually then can raise almost 3 times, because you're going to get 3 moles for every 1 you put in, you're going to have 3. So to sum that up, electrolytes produce more particles when dissolved, so the increased concentration of the solid particles will lower the concentration of the solvent even more than non-electrolytes. So the colligative properties are more greatly affected when we are dealing with electrolytes. So we have to always accommodate and account for that concentration difference. 1 mole of sucrose, no problem, all the math works. You start dealing with sodium chloride, now you're going to have to double some of those concentrations. If it says, hey, you have a 2.5 molar NaCl solution and you're going to have freezing point depression going on, what's going to happen? And then you got to look and say, well, 2.5 molar or molal NaCl is actually going to give me 5 moles of NaCl, Na pluses and Cl minuses, and so I got to use the 5 in my calculations, not the 2.5. With calcium chloride, if you, just to keep the math simple, if you had a 3 molal solution of calcium chloride, well, you put calcium chloride in there and it's going to dissolve. You got to multiply that by 3. So you're going to have a 9 molal solution with your ions. And so you're going to be using the 9 number, not the 3. Okay, moving on. But. 0.1 molal will lower the freezing point nearly twice as much. Notice the word nearly. It does not say exactly. Of course, on paper, as we can always do, we can predict perfect situations, and where they're always called theoretical. This assumes that your ions will dissociate from each other 100%. But in reality, experimentation will always show that you'll never attain theoretical values. You'll never get 100% existing as ions in solution. So it'll almost double, it won't exactly double. The calcium chloride will almost triple, but it will not exactly triple. And it can never do more than, can't go over triple. It'll always be like slightly less than triple. So, it's a difference between on paper and actual experimentation. Not unexpected, right? Okay, so non-electrolyte versus electrolyte, how do you know? Most covalent compounds, for every 1 mole you put in, you get 1 mole floating around. For all soluble ionic compounds, you add 1 mole and you have to then have dissolved ions. And so you're going to minimally have 2 moles of dissolved ions, most likely more. But I do want to include right down here, remember going all the way back to chapter 7, I think, type 4 acids, your binary and your ternary acids. Remember that these actually, while they're covalent, they ionize. And because they ionize, we will treat them as ionic. So hydrogen chloride, you dissolve it in water, and you're going to get hydrogen ions, chloride ions. You've just made hydrochloric acid. So you put 1 mole of HCl in, you're going to get 2 moles of ions floating around. So we will treat it just like an electrolyte. Well, it is an electrolyte. Not just like, it is an electrolyte. So that's what we're going to do. Okay, non-electrolyte versus electrolyte. Ooh, and I color-coded. Can't tell you what the colors are, but I color-coded. So non-electrolyte, 1 molal of sucrose will lower the freezing point to negative 1.86 and raise it to 100.51 on the boiling side. And this is for water. A 1 molal sodium chloride solution, you're going to get a freezing point of negative 3.72 and a boiling point of just slightly over 101. A 1 molal of calcium chloride, look how low we're going now, negative almost over 5.5 negative Celsius, and a 101.53. Aluminum chloride, now we're down to negative 7.44, and the boiling point's creeping up there at 102.04. Aluminum sulfate, well, look at this. 2 aluminums, 3 sulfates floating around in solution. That's a factor of 5. So you put 1 molal in, you have 5 moles of ions floating around. So basically it would be 5 times the sucrose number. 5 times this lower, and then 5 times the 0.51 added to 100 to make it higher. Of course, these are all theoretical. You'll never get them in the lab. You'll never get them if you're actually experimenting. But you'll come close. Moving on. Well, remember that water is not the only solvent. There are many, many other solvents out there that are sometimes very specific and very unique, and sometimes very general. Camphor, for instance, has a normal freezing point and a normal boiling point, as you see, and it has an interesting Kf and Kb value. Notice the Kf, the molal freezing point constant, Negative 39. This is huge. Water was negative 1.86. This is negative 39. So a 1 mol solution with camphor, as far as having a solute in the solvent, it's going to lower it down negative 39 right off the bat. And then it'll raise the boiling point of it there. Phenol has a freezing point of 40.9 Celsius, so it's a solid room temperature. 40 is a very, very hot temperature compared to what we are normally used to. And it would boil at 180, almost 182. Its Kf and Kb values are a lot more in the range of water. Certainly they're higher, so you could say lower, but higher than water numerically. But these are the values for phenol, a different solvent. So just nice for comparison. And I believe there's a table in your book that shows you a few other solvents besides, and there probably is in that mini guide a small table as well that will allow you to do problems with solvents other than water. Molar mass. Okay, so interesting varieties of questions, variations, not varieties. Interesting variations of questions can come up. One could involve molar mass. Because molality is involved, a question could ask to solve for some mass or even some molar mass, we remember, which is grams per mole. Typically, they would couch it as an unknown compound. So that way, you can't just look it up on the periodic table and go, oh, it's carbon tetrachloride, so one of those and 4 of those, and add them up, and there's your molar mass. So here's an example of a solution. A solution of 3.775 grams of X, the infamous chemical X, in 12 grams of water will freeze at a negative 4.72 Celsius. If the empirical formula is C2H2O, remember what empirical formulas are, the simplest whole number ratio of the elements in a compound. So if the empirical formula is that, determine the molar mass and the molecular formula for the infamous X. Hey, look there. I think we got at least a partial solution. So what have I done? Well, I typically go through my problem solving, and in my problem solving, if I have variables, I list them down and I label everything. So here's my 3.775 grams of X. That's the mass. The mass of the solvent, because we have to use kilograms, remember, for molality. So there's my kilogram value. I wrote down the delta T value, and I wrote down, of course, what I knew for water. There's my empirical formula. Here's my question on molar mass, and the molecular formula for X as well. All right, well, where do I start? Delta TF equals KF times the molality, and I don't know molality. So here's molality. Molality is moles of solute over mass of solvent, but I don't know moles of solute. So molar mass equals mass of solute over moles of solute, and that gives me, let's see, just moles of solute, yes, and that gives me molar mass. And I know that if I want to figure out from an empirical to a molecular formula, that's all chapter 6 stuff, by the way, if you want to go back and read it, that you would take the molecular formula and divide it by the empirical formula. My bad, that would be end of chapter 7, not 6. This will give you a multiplier, so you take these two masses, divide them, that multiplier, then you take the empirical formula and actually multiply all the subscripts by that number, and that gives you the final formula. So Z times EF equals molecular formula. All right, so this was part 1. I'm assuming part 2, we should probably run some numbers. Okay, so here we go. Okay, so delta TF equals KF, looking for molality. So I take it over here, rearrange to solve for molality because I do have the delta T and I do have the K value. So because I have these two values, I can plug them in, chug away, and I find the molality. So now I know molality. Okay, if I know molality, that's moles over mass. Well, I have the mass of the solvent as well, and so I can solve for moles of solute. So that's what I did. I'm going to grab my molality, bring it down here. Mass of the solvent was given in the problem, so you can do that calculation, and now I know the moles of solute. So here's the actual unknown X, 0.03045 moles of X. All right, well, I also know that I have grams of X, and now I know what the moles of X are. So here's grams of X given in the problem. Moles of X I solved for just a moment ago. You divide these out, and here is my molar mass of X. 120, almost 124 there. And that's the molar mass of X. It could still be anything, but that's the molar mass. If I want to then know the molecular formula, well, take the molecular formula mass divided by the empirical formula mass, and that'll give me my multiplier. Okay, well, let's come over here. Here's my molecular formula mass divided by the empirical formula mass. Remember, the empirical formula is C2H2O, so I just added all that up. There's that mass. You divide the two, and the number comes up so close to 3 that you just round it to the nearest whole number. Well, that nearest whole number then is your multiplier. So here's your 3 times the empirical formula, and all of the subscript gets multiplied. And I did misspeak a moment ago. I said H2, and it's actually H4. But so you multiply that, and so here's C6. 3 times 2 is 6. 3 times 4 is 12, and 3 times 1 is 3. So the actual formula for X is now C6H12O3, and honestly, I'd have to go look that up to figure out exactly what its name is. But there's your empirical or your molecular formula. We know the molecular formula mass. So we actually have solved this question for the mysterious X. Doo-doo-doo. Okay, so here's an interesting take on the question, and I believe this is where we wrap it up. So I do not have an answer for this question, so I'll leave this hanging and you can look this one up for yourself. So like number 19 in your mini guide, you'd have to check the appropriate chapter. It's going to be about freezing point depression, or I think it's probably called colligative properties. But see, what do we have? What is the freezing point of a 40% by mass aqueous solution of nitric acid? Assume complete ionization, and you could use your mini guide for help solving this one. There is enough information to actually do the question. 40% by mass, it's nitric acid. You can assume 100% ionization, and looking for what the actual freezing point is, and this would be in water, by the way. Okay, I think that pretty much wraps it up. It's been a very long presentation. I didn't think it was going to be this long, but hopefully you stuck with me or you watched it in 2 parts. You can go back through, mute the volume, and get whatever notes you have, or you need rather, that you weren't able to take or you don't have. Otherwise, this wraps it up. I'll deploy just a little bit more practice, I believe, most likely ungraded, and then I'll get a test out to you very, very shortly. Thank you. And of course, always contact me with any questions that you have. Thank you.